Okay, now we assume, let's say we have a planet with a gravitational field. Okay, now we've actually previously done pictures like this that actually show the field lines, and these are the field lines, and then the field vectors getting smaller as you get away from the planet, getting 1/4 as big if you're twice as far from the center of the planet. Okay, well, let's say we want to move from one point in the gravitational field of the planet to another. And let's say we want to move in a straight line. Not something we would ever do. It would be energy, well, not at all energy efficient. It's not the way you move in the gravitational field of planetary and stellar objects. But let's say we did, okay? We want to set up the line integral for the work between here and here. Okay, well, let's say this point is at r1 theta 1, this point is at r2 theta 2, just using polar coordinates for the minute. We see that the angle of your force, and we're going to assume that the gravitational force is the net force, so the angle of your net force with your displacement, with your delta S vector, changes as does the magnitude of the force, so that you're not going to be able to just multiply some force or the dot product of some constant force with your delta S. Okay? Now your delta S is just a straight vector from here to here, but you're going to have to break it up into smaller increments in order to do this integral. Okay, well, the point of this is that the amount of work you're doing per unit of distance is by no means constant here. Okay, so we need to parameterize our path. Okay, so parameterizing a straight line from here to here, well, it's a straight line, so really we kind of want to convert over into rectangular coordinates. The rectangular coordinates from here to here, well, here it's r1 cosine theta 1, r1 sine theta 1, here r2 cosine theta 2, r2 sine theta 2, and that would be our x1, y1, and our x2, y2. So we're going from x1, y1 to x2, y2, where we can see what x1, x2, y1, and y2 are. Okay, well, we want to set up a parameterization. We want t to go from some, maybe from 0 to 1. Okay, that's a fairly typical set of values to use, and maybe that's what we will use. Let's think about what happens as we go from here to here. Vector from this point to this point is x2 minus x1 times I plus y2 minus y1 times j. Well, let's suppose that t kind of represents time, and whatever the unit of time is, we go from here to here in 1 unit of time. Okay, well then, we're at the first point when t equals 0, we're at the second point when t equals 1. The displacement from our first point at t, from our first point, our displacement at clock time t, if we let that be just this expression multiplied by t, then it's going to equal this. Then if t is 0, our displacement from our initial point will be 0, which means we'll be at the initial point. And if t is 1, our displacement from our initial point to our final point is going to be the vector from here to here, so we'll be at our final point. So our position at t is going to be our displacement from the initial point plus the coordinates of our initial point. So that's going to be, well, coordinates of our initial point are x1, y1, right? So our I coordinate is going to be x1 plus x2 minus x1 times t times I, and then the corresponding expression times j. Okay? And we again verify that if t is 0, we're at x1, y1, x1i plus y1j. And if t equals 1, well, you plug in t equals 1, you get x1 plus x2 minus x1. Well, x1 minus x1 0, that's just x2. Plug in t equals 1 here, you're going to get y2. So you're at this point when t equals 1. So this verifies that we have a straight line from here to here. Okay, now we need to find our typical f sub I delta s sub I. Now implicitly we think of partitioning the interval from between t equals 0 and t equals 1. We get a typical ith subinterval, the sample point, and so forth. So the question is, what do we need to partition? We need to partition the t interval. Now I have, in this case, written out the partition of the t interval. 0 equals t naught less than t1 dot 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 less than tn equals 1. Partitioning the interval from 0 to 1. Typical interval has duration delta ti, okay, and sample point ti star. So the question is, what is fi dot delta si for this interval? Well, assume f is the gravitational force function without specifying m1, m2, and big G is a universal constant, incidentally. Okay, so anyhow, all this G, big G, m1, m2 is constant. R changes, and the R vector, of course, changes. So what is Fi and what is delta Si? Well, your Fi is going to be the force that occurs at distance r sub I star. Okay? Where I'm kind of back to the polar coordinate, but r sub I star is just what? It's x sub I star plus y sub I star, right? And that's x of t sub I star, y of t sub I star. Well, that means that your position function is this. Here's your r function, right? Okay? So, to get our position function at our sample time t sub I star, we just plug in t sub I star and we get this mess. Okay? And then that's multiplied by what? Well, it's multiplied by our r vector, which I write here, divided by our r, which is the square root of all the stuff I wrote here. And what I wrote here should be legible. I can read it, but of course I know what it says. Is just this with t replaced by t sub I star. But of course I'm doing the square of the I component plus the square of the j component. So it's going to be this expression squared plus this expression squared with t replaced by t sub I star. Okay, well, that's our typical force. That's our force corresponding to the ith subinterval. That's a force that we get if we take our ith subinterval of our partition of t and use the sample point t sub I star that's between t sub I minus 1 and t sub I. Okay, we'll continue.